Hello, my name is Zachary Lupin. In this short presentation, I'll provide an overview of our manuscript titled A Case Study in Formal Specification and Runtime Verification of a CubeSat Communication System. So let's get into it. First, let's clarify what we mean when we use the term CubeSat. Cube satellites are a relatively new platform for studying space. They are small, compact satellites that are very popular with developers for two main reasons. First, they cost a fraction of what a normal satellite does, and very often are within $1 million budget. Large flagship missions developed by NASA and ESA can cost hundreds of millions of dollars, so that's quite a difference. The second reason these satellites are so popular has to do with the scale of these projects. The lower size and cost means CubeSat projects are generally easier to develop than these flagship missions, and so they have much faster turnaround times, usually a year or two in development, then launch, deployment, and the mission phase. Throughout our study, we refer to all flavors of small satellites as CubeSats, but we recognize that a wide variety exists, mostly dependent on the mass of the satellite itself. CubeSats are miniature satellites, and they still experience many of the issues that large satellites see. The difficulty of launching a working device into space doesn't get any easier by shrinking it down. A communication system is one of the most crucial components for these missions, since it's required in order to transmit telemetry and other information to a ground station. If the communication system fails, that can halt a mission or end it entirely, so communication failures are pretty serious. And it turns out that communication system failures are one of the most common types of failures experienced by CubeSat missions. For this reason, as CubeSats continue to grow in popularity, it's going to be necessary to verify and validate their systems to ensure they perform correctly. To explore this idea, we developed a communication system model using MATLAB and Simulink. This model consists of a virtual CubeSat orbiting the Earth, the orbital simulation component, that sends sample telemetry via a real radio when communication is established, the communications component. The duration of this simulation is 1 virtual week. We calculate communication viability between the CubeSat and a virtual ground station using the link equation in the orbital simulation component of the model. This determination is then used in the communications component to operate a Universal Software Radio Peripheral, or USRP, B210 software-defined radio, or SDR, the SDR's transmitter and receiver, broadcasting a sample telemetry dataset. This telemetry message contains a dozen parameters consisting of CubeSat ID information and radio measurements that would be measured on board a real CubeSat. In addition to the telemetry, this model also outputs the orbital information of the CubeSat throughout the simulation period. The actual setup of this system is shown here. A sample telemetry text file is developed prior to the simulation. As the orbital model proceeds, once a virtual connection is established between the CubeSat and ground station, the USRP B210 SDR transmits the message. A receiving antenna then collects that message, and the PC decodes it and saves it into a data file for later use. For simplification, we used a single USRP B210 connected to a single PC, since it can transmit and receive simultaneously. We now want to verify that the model is operating as we intend. To do this, we must formally specify the system requirements, encoding each into a temporal logic statement. Then we can perform runtime verification with these specifications and the data to examine if each is satisfied during the simulation period. For this case study, our requirements were encoded into mission time linear temporal logic, or MLTL for short. We found this logic to fit perfectly for describing CubeSat requirements, owing to its ability to reason over integer-bounded timelines with Boolean and temporal connectives. A few of these operators are shown here. The orbital nature of CubeSats requires a logic that reasons with integer-bounded timelines. The CubeSat will make orbits that do not pass over the ground station, or will only do so for a short amount of time. A CubeSat with a 90-minute orbit, as an example, will not be able to send down telemetry every 90 minutes. We used the Realizable, Responsive, Unobtrusive Unit, or R2U2, as our RV engine for this study. CubeSats are known for having relatively low computing power, so an unobtrusive tool is very necessary to perform RV for such projects. R2U2 also possesses a scalable and extensible framework, allowing for expansion of the study in future work. Going back to our setup slide, An additional portion is added showing how RV fits into our setup. As said before, we have our starting telemetry file that is transmitted during the simulation with the USRP B210 SDR. The signal gets received and then saved to a file. Recall that the orbital information is also saved. These datasets are then run through R2U2 with our specifications to determine if the system requirements are satisfied over time. We'll now take a look at two specifications in detail and the corresponding RV output. Our first specification states that communication between the spacecraft and ground station can only occur when the spacecraft is above the horizon, i.e., when line of sight is apparent. This is encoded into an MLTL specification with two atomic propositions, one saying that the connection status is active, and one saying that the elevation is above 0. We then develop a spec saying globally phi2 implies phi1. Note that we also implement a temporal operator 0 to 3 to account for occasional off-nominal data points. Comparing the orbital data of the connection against the specification, as shown on the left side of this figure, we see that it is satisfied at all time steps for a nominal dataset. On the right side of the figure, we purposefully injected faults into the dataset to check if the RV output would detect a violation, which it did. Now we examine a specification measuring a voltage line in the telemetry set. This specification states that the radio's 3.3 volt line must not vary more than 10% from its desired 3.3 volt value. It also mustn't vary more than 0.5 volts from the previous time step. This is encoded into an MLTL specification with 3 atomic propositions, one saying the voltage must not exceed a maximum, one saying it cannot go below a minimum, and one checking the previous time steps voltage measurement. We then develop a spec saying globally, phi1 and phi2 and psi must be true. Again, a temporal operator 0 to 3 is used to account for occasional off-nominal data points. On the left side of the figure, we see a nominal dataset, which R2U2 verifies to be satisfying this spec at all time steps. In the center, we see a couple off-nominal data points. However, a fault is not flagged because of the temporal operators. On the right side of the figure, we simulate a failure of the voltage line, and R2U2 correctly identifies a fault. With this paper, we have developed a reference set of formal specifications in mission time linear temporal logic, MLTL again, that describe a CubeSat communication system. We detail our validation of these specs and discuss patterns observed while writing and revising them. We further discuss our lessons learned from validating these specs, and that will inform future CubeSat RV efforts. In future work, we will apply our methods to other CubeSat subsystems, exploring their requirements. We also plan to investigate analyzing a full CubeSat telemetry dataset, since we minimize the telemetry message for this case study. A full CubeSat message could consist of hundreds of parameters, and so there's a lot to work out there. And of course, we hope to eventually apply these methods to a real CubeSat, ultimately demonstrating that verification and validation can lend to better performance and better operation of these systems. Thank you.